So let's do some applications of Gauss's law. These are some standard things that everybody does in physics classes, and everyone assumes that you can do in physics classes, even though your need to do them will be only moderate at best. But it's worth walking through. All right, for practice, consider an infinite line of charge with linear charge density lambda, as shown below. Draw a useful Gaussian surface, a thing that would let us apply Gauss's law easily. And as a hint, remember, you want to think about what the shape of the electric field is going to be like. You'd like your Gaussian surface to mimic that shape, or at least be the same symmetries, and the symmetry of your charge distribution. Well, you might remember that we discovered that the charge density that's linear like this produces field lines that are radially outward only. I'm just going to put a few of them. There obviously would be as many as you'd want, but they come out. And although I'm not great at it, if we sort of imagine we have our three axes like this, then there would be some field coming out that way as well. This is hard to do three-dimensional sketching on a two-dimensional surface. And a useful Gaussian surface then would be one which is piercing these, but then follows the symmetry of the charge distribution. In other words, some sort of cylinder. That's not a really good cylinder, so I'm going to redraw it, but redraw it not talking. So we want a cylinder that looks something like this, because then our electric field will be piercing that cylinder everywhere perpendicular. Mocked up in Google document drawing tools, maybe something like this. All right, so a cylindrical Gaussian surface surrounds an infinite line of charge. The flux phi sub e through the wall of the cylinder is one of these following things. Remember the definition of electric flux, which is the electric flux is the integral over a complete surface of E dot dA. Things are a little tricky though, because there are actually three surfaces here. This is a cylinder, so let's continue this guy. Remember, there's a cap back here. There are actually three caps, or three surfaces. There is cap 1, there is cap 2, and then there's the wall. So when we say that our flux is the integral of E dot dA, it's really going to be the integral of over cap 1 of E dot dA plus the integral over cap 2 of E dot dA plus the integral over the walls of E dot dA. But here's our trick. We know that the electric field is coming out radially from the line, which means that it slides along the cap, but not through the cap. So the electric field dotted into dA, well, dA, let's just draw our cap for the moment. Here's our cap. The electric field is going like this or like that, but dA points perpendicular to the surface. And two vectors that are dotted into each other, when they're perpendicular, have a dot product of 0. There's no flux through the cap. It slides along the edge of the cap, if you want to think of it that way, but it doesn't go through. It doesn't enter or leave the cylinder. And likewise for the back cap. So the only thing that's going to matter is E dot dA over the walls, but on the wall, the electric field is constant. Its direction changes, but its strength is constant, and it's always in the same direction as dA, because dA is going to be perpendicular, but the electric field is also now perpendicular to the surface. And that means E dot dA, for that case, is just 1. So this becomes the integral over the wall of E dA. But the electric field is constant on the wall. I've run out of good room here. Let's go down here. So this integral, the flux now is, I can bring the E out, and now I just have the area of the wall. The area of a cylinder of radius r and length L is you take the circumference of the circle, 2 pi r, and stretch it out by the length, so times L. So our flux should be 2 pi r L E, this one. All right, and that says use that result. What result? That phi sub E is 2 pi r L E. Use that result in Gauss's law to find the strength E of the electric field at distance r from the line. So we know Gauss's law tells us that the electric flux is the enclosed charge over epsilon naught. How much charge is enclosed? Well, remember that lambda is Q over L. Now for us, this is an infinite length charge, so there's an infinite amount of charge in the whole line, but I don't care about the whole line, right? That's the whole line. I only care about the charge enclosed in my cylinder, which is, this length of charge. And so Q enclosed is going to be L times lambda. So now I have over here 2 pi r L times E. Oops. And that equals L times lambda over epsilon naught. So we can solve for the electric field by dividing everybody by 2 pi r L. The L's cancel out, and we get lambda over 2 pi epsilon naught r, a result we had before, and now we have again. All right, different case. From symmetry, we know that the electric field due to an infinite sheet of charge points away from the sheet. We actually know the field from direct integration, which we did before. Let's pretend for the moment that we didn't. You might remember the integration. It was a little messy. We had to get a ring of charge and then a disk of charge and then let the disk become infinitely large. Instead, let's do this. Let's take a Gaussian surface, a cylinder, which punches through like a straw through the sheet. And let's make that the cylinder be bisected by the sheet, and let's let the area of the end caps be A. And the area of this would be something related to the length and the radius. Let's assume that the charge sheet has surface density charge sigma. So here's our geometry. Most important thing about the geometry is notice that the electric field is pointing away, and for the caps, the element of area is also pointing away. All right, the charge enclosed in this little region here is sigma times A. And the flux through the curved part of the cylinder is 0 because the field lines are always now parallel. Again, they're not piercing the walls of the cylinder because the electric field is perpendicular to the normal vector. We get 0 dot. The electric field is constant on each end cap due to the symmetry. Why? Because we picked the same distance. So even if it varied with distance, we're the same distance away, and we could never tell which side we're on, so it must be the field is the same, but points outward. And in both cases, points parallel to the normal vector. So we can compute the flux pretty straightforwardly. The flux is the integral over the closed surface of the whole cylinder, E dot dA, but we can integrate over the two caps, cap 1 and cap 2, and the side. The side, of course, as argued before, E dot dA is 0, and therefore there is no flux through the sides. And that each of these, E dot dA, is just EdA. So I can just pull EdA out of both of them, which means I get EA plus EA, or the flux through the surface is 2EA. But the flux through the surface is also the enclosed charge over epsilon naught, and the enclosed charge was sigma times A. Putting all of that together, we get that sigma A over epsilon naught is 2EA, or once again, notice that the area of the surface drops out, and it had better. It was arbitrary. We just made it up. And we're left with the electric field is sigma over 2 epsilon naught. This is, of course, the result we had before. But remember that the process before was pretty grungy and had some weird, hey, let things go to infinity in them. And here it comes very, very straightforward, arguing just from the symmetry. And that's the general truism for Gauss's law. If we have a symmetry that we can exploit, then Gauss's law will let us get things very, very quickly.